All right, let's start talking about beam notation, just a general notation that we're going to use in beams. Again, we're going to be using formulas and whatnot, throughout these next couple weeks. I mean, when we get to the formulas, they're going to have symbols, terms in them. Let's know what they are. All right. We're going to deal with rectangular beams. And generally, we deal with a beam that's called a singly reinforced beam, and that means it just has steel down on the tension side. In reality, when you get to commercial construction, you'll probably have steel on both sides of the beam. Steel on the tension side, steel on the compression side. That's fine. Most designers, when they have steel on the compression side, they use, they almost neglect it. I mean, it helps us out, but it's on the compression side of the beam. Steel's really good in tension. That's what we consider. In compression, it helps us for like deflection. It helps minimize deflection. And you might say, well, why did they even put it there if it's just used for deflection? You got to remember, for our beams, in commercial construction, they're not typically simply supported beams, but they're beams that, again, frame into monolithically cast with columns, and so they go over, from column to column, but they're rigidly tied into that column. That means that beam has a tension side on the top of the beam at the columns, and it has a tension side on the bottom of the beam out there in the middle. So it's common that we run steel both top and bottom, not the same steel, but steel top and bottom. Okay, but we sort of talk just about simply supported beams. Anyway, notation. The beam, the rectangular beam, is going to have a width. And we call that width, or we label that width, B. Okay, which, again, that makes sense. We've seen that before. All right? The beam is going to have an overall depth. Some people say height, and we're going to call that H. Now again, notice I said overall depth or overall height. Okay? Beam's going to have some steel in it. That steel, what we're most interested in design, is the area of the steel. And the area of the steel is going to be labeled A sub S. So capital A, subscript S, A sub S, area of the steel. Okay? Another depth that's really important, I mean, the overall depth's important, but for our design calculations, the depth that is going to be more important is what they call the effective depth, or some people call it the design depth, and they give it the letter D. And the design depth, or the effective depth, goes from the compression surface of our beam down to the centroid of the steel. The effective depth, or some people call this the design depth, goes from the compression side of the beam down to the centroid of the steel. Okay?
So in some cases it'll be on the bottom instead of the top.
Yeah, I mean, if your compression side was down here, yeah, it'd be going the other way, right? Okay. We'll only consider, just one value. I mean, in a real situation, real life, like I said, most of the time in commercial construction, those beams are monolithically cast into columns, so that beam is not simply supported like we would assume. like we will assume in here, but it's a, a fixed beam, so therefore it has tension on the top, on right next to the columns, but out in the middle it'll have tension on the bottom. Again, now I did say down to the centroid of the steel. Okay, there will be a problem or two that you get somewhere along the line where your tension side has double layers in it, which again is common in commercial construction. They have a beam, but they won't be able to fit all the steel in one layer, so they just double layer it. Okay, D just goes down to the centroid of the steel. Okay, so again, it doesn't have to be to the centroid of a layer. If you have two layers, it's the centroid of both layers, so between the layers. All right. Every once in a while, I mean, we'll get into this. This is still probably coming up later on, or a little while from now, but there will be, in most beams, another steel member. And again, this is going to be our topic, a couple weeks from now, but it's going to be a U-shaped bar. So you might even, especially when we get to the design of beams, they might say, oh, and this beam has like a number 3 stirrup, okay? And they're just telling you that. That doesn't have anything to do with our bending moment capacity for our beam right now, but they're going to tell you that because you might want to know this distance here. And that distance from the edge of the beam to the steel, and then if it was the stirrup, if that was the first steel that there was, they would call this clear cover. Or some people would just say the cover on the beam. Now the ACI code gives, and we'll talk about this later, various values for cover. Cover basically is, what do you think its purpose it serves? Huh? Well, it covers the steel, so in fact it's doing what? It's protecting the steel. Okay? Protecting the steel, covering the steel, protecting it, possibly from, chloride intrusion, so the steel doesn't rust. I mean, that's one of the big things we try to do, like on, with bridges. I mean, bridges, you're going to see a higher cover than you would see in a building like this because, well, you're under a more severe environment, I mean, if you're inside a building, the environment's pretty constant. If you've got a bad environment or a detrimental environment, you're going to see that cover get bigger. Now again, so there could be a few more things. Again, how big is the stirrup? You'd like to know that, because a lot of times when you get into design, you'll just come up with what's the overall depth, but ultimately when you do start doing your calculations, this effective depth is going to be important. Okay, so anyway, you will hear people talk about cover or clear cover. I should probably point out too, I mean, my drawing is really bad up here, but cover is not just to the bottom of the beam. There's actually cover to the side of the beam too, and that's clear cover. So I mean, don't think that cover always means to the bottom. It could be to the sides, it could be to the top of the beam, whatever we're talking about. Cover could be on a column where we're looking at, bars to the edge of the column. Cover could be in a footing where you're looking at bars to the bottom or the side or the top of the footing. So I mean, this cover concept goes beyond just this bad drawing that I gave you. It's it goes many other places. All right. So notation, beam notation. Anything there? Now the other thing, we already know this is not necessarily just beam notation, but other notation I give you when I say F prime C. What's that? That's the design concrete's compressive strength at a certain day. Day would be what? 28 days, unless somebody says it's something different. We also know this notation, F sub y, right? That's the notation for what? Yield strength of the steel. So there's other notation that you have along with there.